Welcome back to my Modern Java by Example webinar series. Today we're going to be discussing other aspects related to back pressure and flow control in the context of Project Reactor. This example is something we've looked at before, but I've added a bunch of new features to it. And so we'll look at the code, we'll run it to see what the different behaviors are. But to start out with, of course, we're first going to see where you can find all the code. So let me start by sharing my screen. And we'll be off. So the code that we'll be looking at today is once again in the Reactor folder under EX3. And as is often the case, I've added lots of new enhancements to it since the last time we got together and chatted. So without any further ado, let's go ahead and take a look at the code. So here's the project. The particular part we're going to focus on today is run tests. Or run test, I guess it really is. And you can see that that's this method here. First of all, just a quick recap, this program generates a bunch of random integers within a range that you can set. And then it goes ahead and it checks to see whether those integers are prime. So it's basically emulating a sensors type system where data is flowing in, and then you have to process the data in some way. So that's kind of what we're approximating. So here's the main part of the driver program. We have a method called publish, which is what's going to generate the data. And there's some cool new enhancements to publish that you'll see here in a minute that are really fun and give us a chance to demonstrate these different back pressure strategies under different circumstances. Then what happens once you start publishing, we're going to have a function called determine primality. And what this is going to do is for every random number that we've generated, we're going to go ahead and emit the number. We're going to publish on the subscriber scheduler, which could be different from the publisher scheduler or could not be. They could both be the same scheduler. And then we'll see another enhancement I added is now we can actually have a multi-threaded subscriber. So we can have multiple threads that are pulling the data through this and processing it, or I guess having the data pushed to it concurrently. For every number that we emit from just, we're going to go ahead and check to see if that number is prime using our prime checker. In the last couple sessions, we've talked about prime checkers. We've talked about the mechanisms that are used to do different types of memoizations, untimed memoizers, different variations of time memoizers, no memoizer at all. We're not going to talk about any of that stuff today, but that's still, of course, under the hood, making the program cache the data in certain circumstances to speed things up. So here's the main Flux pipeline. We're going to take the results that come from the publisher, and then we're going to transform them so we can conditionally log them using the logging mechanisms that are provided by Project Reactor. I may or may not turn those on. They're primarily interesting just to see the way in which the events are emitted. And then we're going to go ahead and do Flatmap. Now, this is where the code diverges from what we had before. Before, we had at most one publisher thread and one subscriber thread. And now what we're going to be able to do is we'll have one publisher thread, but we can have multiple subscriber threads, and we want those subscriber threads to run concurrently. And so the way we're going to do that is by using the Flatmap idiom that Project Reactor and RxJava are famous for to allow the code to run in parallel under the right configuration choices. And we'll take a look at that in a second. We then have a subscriber, and it's going to subscribe something that we call the hybrid back pressure subscriber, and it can conditionally decide to use back pressure or not, and we'll see how that works in a second. I should probably rename that class because it's not always a hybrid back pressure subscriber anymore, but it can play that role when we need it to. So that's the main pipeline. We're going to do a deep dive in some of these things and look at some new capabilities for dealing with different types of back pressure strategies that Project Reactor supports. And then we have the main thread, just wait for everything else to finish, and then we print all the results. Again, I'm not going to spend a lot of time going through the parts we've already talked about. So let's go ahead and take a look at a couple things. Let's start by taking a look at the publisher. So the publisher is what's set by the publish method. The publish method is now very different. I've very carefully refactored it so it does a lot of cool things. So let's just kind of take a look at what it does. So it's going to use the Flux create factory method. And we're going to use this to either create a back pressure enabled emission of random integers, or not. And what we're going to do is going to be dependent on the BackPressureEnabled flag. So you can set BackPressureEnabled if you want to. And just to reiterate how you do that, if you open up the command line, you can see that one of the flags that you can set here is -B to be true or false. So if you set it to true, then BackPressure will be enabled. If you set it to false, it won't. So if we go with the BackPressureEnabled model, which is actually what we looked at last time, then we use this factor method called MakeBackPressureEmitter. And it's given an iterator to all the random integers that we generated. So let's go take a quick look at MakeBackPressureEmitter. This is pretty much what we had before. And so we're just going to go through it very quickly. But I want you to at least be able to compare and contrast the way that you make emitters that are BackPressure or push-pull hybrid model aware versus just, let's go ahead and blast the data through. So this approach allows BackPressure to be invoked or enabled. And the way it does it is it takes the flux sink. So what this parameter is a flux sink. And you can see that if we wanted to expand it. So it's a flux sink. And so we're going to use the onRequest method. And this is the method that's used by downstream operations, such as the subscriber, for example, in order to pull data through the stream. So that's what we looked at before. So when this gets called, it's going to tell us I've got a request for this much size. And then what it's going to do, it's going to go through and try to get that many items that were requested. And it uses the iterator to do that. And we go ahead and basically do next, 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 next until either we've gone through the size of this particular call or we've run out of items to iterate over. If we have gone through as many things that were requested in this particular call, we're going to keep going next time. If we've exhausted everything in the iterator, then we go ahead and do the sync complete. Okay, so that's basically the version that is aware of BackPressure. The new version, which I added, is called Make Non-BackPressureEmitter. And it also takes the iterator. And here's what Make Non-BackPressureEmitter does. It doesn't use the onRequest method. So instead, it's just going to be an emitter that's just going to blast the data out just as quickly as it can. And the way it's going to do that is while there's anything left in the iterator, it's going to go through and get the next item, and then it's going to go ahead and publish the next item. So it's going to keep going. And this particular comment is no longer correct. It just publishes the next item unilaterally. So it's going to go ahead and try to blast everything out. And then when it's all done, emitting everything, then it sets the sync to complete. So it says, if I'm all done at this point, then I'm going to go ahead and complete. Okay, so that's the new emitter. And that's important because when we see the strategies that we're going to use here, they're largely going to be based on the non-BackPressure emitter. So let's go ahead and take a look at what those strategies are, and that'll take us back up here. So what we're doing, the second parameter to create, if you so choose to provide it, allows you to specify the overflow strategy. So let's go take a look at what the overflow strategies are. And there are 5 overflow strategies that come baked into Project Reactor and RxJava for that matter. And they're basically drop, buffer, error, ignore, and latest. And so we're going to kind of show these and how they work. The drop overflow strategy says if we start getting to the point where our buffer is full, just drop the next item that comes along. So if the next item that comes along, drop that one, and then keep the other ones in the buffer, and they'll eventually get processed, conceivably. Latest is kind of like drop, except it reverses things. So it says if we've got to drop something, keep the latest item, and then drop one of the other ones, or drop other ones. Ignore says, the heck with it, I'm ignoring this. I'm not going to care if I run out of memory. I run out of memory. So so what? Buffer basically says buffer the data, and then error says throw an overflow exception. And so overflow says we're running out of space, so we need to deal with that. Okay, so those are basically the 5 different strategies, and of course I've made it so you can configure them via the command line options. So if you come up here and look at the command line options, you can see that one of the options is -O, little o, And then you can put in D for debug and I for ignore and B for buffer and so on and so forth. Okay, so that's basically how that's going to work. And then we're going to see when we run the program that we get slightly different behavior under different circumstances, depending on what strategies we select. So this is probably, let's see if there's anything else I want to say before I run the program. So coming back over here, I have this error resume in here for now. This is sort of a placeholder as I figure out how to deal with a little quirk with RxJava, with Project Reactor, and dealing with exceptions that are thrown in threads running in schedulers. But we'll talk about that later. So keep in mind that we're going to go create this flow, this flux stream of integers, and then we're going to subscribe on the scheduler. And if you recall from before, when the program is actually initialized, we have some clever logic to decide what thread or threads to run the publisher and all the subscribers on. So you can see here the way we do it is we go ahead and we make the publisher run in one thread. Now we could have the publisher run in multiple threads, but I'm trying to keep it simple. So the publisher runs in one thread, and believe me, it can spit out data in one thread way faster than one or more subscribers can keep up, because the subscribers have to do this complicated prime checking logic, which tends to slow them down, as you can imagine, especially as the numbers get big. Then we come down here and we say, are we trying to run in parallel or not? That's the minus little p option that you have on the command line. So if you look back up here, minus little p is either true or false. Right now, I have minus little p set to true. And if we're running in parallel, then we're going to make ourselves a new pool that runs the subscriber in. And then we also have a new option I added called parallelism. And you can set what parallelism is. Right now, parallelism is set to 1, but I can set it to n, where n is something higher than 1. And as you can see here, what I can do is I can basically make a pool of threads, and then I can have those threads, that pool of threads, running the logic to do the publish on operation for each of the numbers that are pushed through here. So that's how we can basically have a pool of numbers that will do the processing, which is very cool. Okay, so if we're running with the parallel option, then we get a separate scheduler. If we're running with the non-parallel option, then the publisher and the subscriber run in the same thread. Just want to make that clear, because otherwise the results won't make any sense. Okay, so let's come back down here. Here's the program. Let's go ahead and run it, and you can see what it's going to do. So the way I'm setting this up for the first run is we've got debugging turned on. We are running in parallel, so the publisher and subscriber are on different threads. We're going to have one thread running the subscriber pool at the moment. We'll change that easily, of course. We're going to be doing no back pressure at all here. So this is the emitter that just spews it out as quickly as it possibly can. And then we're going to go ahead and generate 100 values, which are going to be very large. And we're going to turn off logging. We're going to use the untimed memoizer. And we're going to do the ignore strategy. So this should pretty much work the way things normally would work. And then we also have this really cool thing that I wrote that lets me selectively debug certain modules using tags to select them. So we're going to see the publisher and subscriber logic. So let's go ahead and run this stuff. And it'll crank for a little bit. As you can see, it didn't take too long to run. And here's what it's doing. You can see it's generating 100 items, and it's going to go ahead and basically just spew them all out, because there's no flow control here. It just, boom, it's all going. And then after everything gets spewed out by the publisher, then the subscriber thread starts to process it. You can see that there's no back pressure going on here at all. And we ended up with 63 prime checks with 37 duplicates for our memoizer, which is untimed. And then we have a version that doesn't have the memoizers. And you can see that the stuff's still running in the background, as it goes along. Okay, so that's basically the way that this works. I would ignore the timing results. This is really just to show that we're just blasting it through. And notice that we ended up having 100 prime checks. So everything came through. Now let's go ahead and let's change this to use the drop strategy. So that's the D, minus OD. And what this should do, and it may be hard to see it from the way it's looking here. We'll see how it behaves. But what it should be doing is it should be dropping stuff, and we'll see if we end up with as many counts as at the end when we're all done, because it should be dropping some of the values. So remember, before we had a count of 100, and now, as you can see, let's see. I see the problem. We have to actually generate more elements than the buffer size can handle. So let's make that 300. I think by default, the buffer size is something like 256 or something like that. So this should hopefully show the dropping. So what happens when it drops, of course, is you don't end up getting all the elements going through. And when something comes along and the queue is full, the latest item to be processed is just going to be dropped off the end. And so this takes a while to run, because obviously these are large numbers. I should probably make the numbers a little slower. You'll also notice that we only have one thread that is doing the prime number processing, and that's the thread that's running in subscriber 2. And so this is taking quite a while to run. But basically, the point of this is that it's going to be doing this only in one thread. And so as a result, or the subscribing and the processing is only being done in one thread. So that's what's taking all the time. Let's see if it can finish here in a short order. So what we will hopefully see here is that some of the items got dropped. If they don't get dropped with this model, I'll run it with a slightly different set of parameters in order to show what happens when it drops. But remember that when something's dropped, the latest item is dropped. So the queue already has a pot of stuff in it, and then the later items get dropped. This is definitely taking a long time to run. So while we're waiting for that thing to finish, I'll come back over here and again, just sort of give you the high-level view of how that's getting done. And maybe it's done by now. Then what I also want to do is show you what happens when we run this with multi-threading, and I think you'll see it's a lot faster. So what you can see here, this is really interesting, right? So take a look at this. Remember I told you that there's internal buffers that have 256 elements in them. And so what happens, and this is just the preset defaults that come out of the box with Project Reactor. I think you can control these buffers to some extent through various operations, but what you get out of the box is 256. So as you can see here, we only were able to process 256 prime checks with this approach, because once it got to that stage, because the publisher was generating the data way faster than the subscriber could keep up, then it would start to drop everything that came after that. So this is demonstrating the drop option. Let's keep drop enabled, and let's go ahead and crank up the number of threads and see if that can make a difference in terms of, number one, how fast this gets done, and also in terms of how much stuff gets dropped. We'll see if we have to drop as many things. So -P8, so now we've got basically 8 threads in our pool. They probably won't all be used, but they could be used. And what you should see here, first of all, you notice that all the publisher stuff got spewed out really quickly. But then what we should see on the subscriber side, you can see that there are different numbers showing up for the threads. So what this is saying is that different threads are processing those different items that are being emitted through there. So once again, you can kind of see there's an interleaving, and things are running on subscriber 2 and subscriber 9 and subscriber 7 and so on. So we should see those showing up here in a second. There's subscriber 9 thread. So we're getting a little bit of benefit from having multi-threading going on my 4-core hyper-threaded machine. And once again, however, it's funny, we still ran out of this. We still ran out of the items, right? We still ended up having to drop the items, but conceivably it ran faster. And in fact, we can actually demonstrate that to ourselves by coming over here and turning off debugging, because otherwise it spends all of its time, wastes all of its time writing to the screen. And let's go ahead and run this with 1 thread for the subscriber, and we'll do 100 items now. Let's do 150 items. That should give a good result. So here's the run with, oops, sorry, it canceled that. I want to change the configuration back here to not drop anything. So let's just say I want to ignore instead of drop. And so now it's going to go ahead and run with 150 items, which shouldn't take too long to run. The first run here only has a single thread running as the subscriber. So it has to, the publisher is also running in a different thread. As you can imagine, it's just tossing the data willy-nilly, helter-skelter at the subscriber. And now we're running it without the memoizer. And we'll see kind of what the timing results are without having anything more than one publisher and one subscriber. And that should finish here momentarily. And then we'll rerun it and we'll crank up the number of threads. I also have a 6-core machine with multi-threaded or hyper-threaded cores, and that definitely chugs through this stuff pretty fast when I turn on the parallelism count to be higher. Okay, so the number I want you to remember is basically 21,000 milliseconds with the memoizer enabled and 29,000 milliseconds with the memoizer disabled. That's about what we'd expect. And then let's come over here and let's turn on, say, 8 threads. I don't think we'll use all of those threads, probably more like 7 of them. But let's see what we do. So now we've got things running in parallel. And this is a great example, of course, of an embarrassingly parallel application because the computing the different primes have no dependencies on each other, so they can all run at the same time. So let's see if this will run a little faster. The input data is not quite the same, and sometimes that can influence things, but this will at least give us a kind of a smoke test comparison between the two approaches. And as you can see here, the version with the memoizer was about twice as fast, and the version without the memoizer was about maybe 1/3 faster. And I think the reason for that is just that there are some primes in there, and so those take a while to compute, especially if we haven't, especially if they're duplicate primes, where we would get a lot of win by not having to recompute them if we use the memoizer version. So turning on the more threads, it does in fact speed things up a bit here, but of course it's all dependent on other factors like how long the primes take to run and so on, and how many primes there are. Okay, so a couple other options that we can also demonstrate. It's a little hard to see this. I haven't quite figured out how to do the test to demonstrate this, but we could also put an L in here. And if we put an L in here, then what's going to happen is we're going to end up, whoops, let's not run it quite so long. Let's do it maybe 100 iterations. That's a lot faster. So let's go ahead and run this again. And now we have the L or the latest flag enabled. And what that says is when the buffer is full, when the publisher finds the buffer's full, it arranges so that the latest item is going to be the one handled by the subscriber, not just dropping it. And what you can see here, this particular case, it looks like we didn't actually drop anything. And that's because we didn't make this big enough. Let's see, let me kind of crank down the max size a bit because it takes too long to run otherwise. Calculating those big prime numbers takes a long time. This should go very fast. So you can see here that we had 300 elements, but we only managed to actually process 257 of them, and that's because we had the latest flag enabled as the overflow strategy. And I haven't got this shown here easily, but if we were to take a look at the output, we would find that the elements that came through with the latest strategy would be different from the elements that came through with the drop strategy. And then the last thing I want to show you, and I'm still working on this, and so any tips would be appreciated. Let's turn on the error strategy. So what error does, and I think what I'm going to do for this, to demonstrate this, I'm going to turn on logging. So now I'm using the underlying logging mechanisms that we get with Project Reactor. And let's see. Let's give it a big lot of these things. And maybe take out any parallelism. So let's go back to parallelism equals 1. And let's make a lot of these. And hopefully this is enough to trigger the exception that I'm hoping to get. Let me try one more thing. So I've had a little bit of a quirk with Project Reactor and what happens when exceptions are thrown. So let's comment out this little trick, which is converting an exception into something else, and see if we can get it. There we go. Now it's blowing up. That's what I want. Strange when you actually want to get an exception. So what's happening here is with this model, with the exception model enabled, when the buffer gets full and the next item goes to put something in the buffer, then that causes Project Reactor to generate the exception overflow, or the overflow exception. And this says, as you can see, the receiver is overrun by more signals than expected because we've got a bounded queue. And that causes everything to blow up, which is what we want at some level. And you can see what comes back here is a failure message because we didn't succeed. And that's also what you'd expect. The tricky part, and I'm still kind of wrestling with this, is how to catch that exception. So I can throw the exception, but then it blows everything up. I can convert the exception into just some other value, which is the on-error resume mechanism. But I'm still working on ways to both catch the exception and then have it work without blowing up the program. So that's still work in progress. But this is one of those weird things with RxJava or Project Reactor where the documentation is almost entirely silent on what happens when exceptions are thrown in this circumstance. So I'll figure it out and I'll let you guys know about how it works later. Here's where the problem's actually coming from. It's this call here. When the exception is thrown, then that's going to cause the emitter to realize that the subscriber's gone away basically because it got an exception. And this will then throw an exception. So I have to find a way to catch that, but still propagate it as an error up through the flux chain to the subscriber to handle it properly. Okay, so those are the main things I wanted to show you today. So the key points here are that with RxJava, you can designate the control flow strategy. It's basically the BackPressure strategy, or the overflow strategy. And that's very important when you have emitters that don't have BackPressure enabled. Now, if we turn on the BackPressure version of all this stuff, so over here, you take a look, I had the BackPressure flag set to false. So if I go through and change that to true, then knock on wood, we shouldn't see any of these problems because in this case, it's not emitting a gigantic amount of data. So it's just emitting, windows of data. Whoops. Let's go over here. Turn off that error flag. Let's go ahead and say buffer, for example. So in this particular case, now it hopefully won't throw an error. And that's because it should be using the emitter here. Yeah, now you can see it's doing it in a much more sensible way. Let me turn off logging. That'll get annoying for 30,000 of these things. Let's see. Let's change logging to false. And let's change BackPressure to true. So now we want to turn on BackPressure and we want to turn off logging. And in this case, it should go ahead and process in a much more sane way because it's not trying to, the publisher's not trying to ram all the items in one fell swoop. So let's see how this is going to work and whether it's going to do something sensible. Let's see. Crank down this numbers of these things because that's going to take a while to run. Let's also turn on debugging so we can actually see what it's doing. Now let's try running it. I'm really happy with my little driver program because it's got all these various options you can tweak and twist and so on. And it gives me a lot of control over showing these things. So, all right, so now it's doing sensible things. So as you can see, it's going through here, and it's requesting chunks at a time. So you can see that in this case, I think they're never more than, let's see. If you take a look at the pending items, you'll see that they should really never go above 255. And that's because if we go way, way back to the very top, let's see if it's still in the buffer. It is. That's the request size that we're doing. So now we've switched over to the hybrid push-pull subscriber model of BackPressure. And the request size is 256. And so as you can see here, the number of pending items is never more than 256 because we've turned on the hybrid push-pull BackPressure mode or model, which is great. And if you take a look back here, this is something else I added since we looked at this before. You look at the hybrid BackPressure subscriber. I have this little clever technique in here where if BackPressure is enabled, we go ahead and compute 70% of the request size. And so what we're doing here is we're going to request the next tranche of data when we've consumed 70% of the data that was in our window. And the idea here is kind of do a little prefetching. So we're not quite done with our processing, but we want to request the next chunk because that way the pipeline stays full. So anyway, that's just another variant of BackPressure. Depending on what you're trying to do, if you're trying to protect your buffer sizes and protect your subscribers from being overrun, the hybrid model, the hybrid push-pull model is probably the way to go. And I think you can agree that if you take a look at the little driver program I had here, it's real trivial to switch back and forth between an emitter that emits using the BackPressure, the hybrid push-pull model, and an emitter that doesn't. So you really need all those different options for the overflow strategy for emitters that don't do the push-pull model. But if you're using the push-pull model, there's really not a lot of reason to have to turn on those other strategies because you shouldn't be overrunning your buffers in the first place under that model. So hopefully you can see that there's lots of interesting variation and variability in Project Reactor and RxJava for that matter to give you a lot of control over all these different features. So with that, let's go ahead and come over here and take any questions that people have. Let's see. All right. Who keeps the buffer? So the buffering is done internally to the various stages in Project Reactor in a pipeline. So you can basically think of it as sort of this is not quite the right analogy from the implementation point of view, but think of it sort of like the pipes and filters pattern in a Unix pipeline where you have a supplier and it generates data and it goes through a pipe, that vertical bar on the command line. And that basically is a sort of a buffer that the kernel manages. And then it goes to the next phase in the pipeline, the filter, if you will. And so you can think of these things as being buffered up along the way as they move through the different layers. And different operations buffer things in different ways. And you get a tremendous amount of control if you choose to exert it over those different layers. Why is there no option to block on the overflow? Well, block on the overflow, I think what you mean by that is have the emitter not emit. And that's basically what the hybrid push-pull model would be. So what that says is, don't push the next tranche until you've got the various pieces here that you need. What aspect of the code enables multiple consumer threads? So let me go back to show that because that's important to understand. So here's the part of the code that is controlling this. And this, by the way, is just good old Project Reactor or RxJava logic. There's nothing particularly tricky about this. This is just me integrating these things in the proper way. So here's the stream. Remember, the publisher is running in its own thread. It's running in its own scheduler, which in this case we call publisher because it used subscribe on. And then up here we have the stream, the pipeline. And this is that good old Flatmap idiom that we always talk about with RxJava and Project Reactor. So Flatmap, when used with this little determine primality function, which is just made it easier to read the code. I could have integrated all this logic in line with Flatmap. But what we're doing is we're saying for every number, emit that number and then publish on the subscriber scheduler. And the subscriber scheduler here either has one thread or n threads. And we can control how many threads are going to be used by the flag that we set up here called options instance parallelism. And all that's doing is just returning the field here, which I set initially to 1, but then if you choose to, you can override it down here on a command line. So if you give the -P option, then it sets parallelism to whatever you want it to be. So that's how it's getting set. We're setting it on the command line, saying I want to turn this thing to be the parallelism version, and here's the count that I want it to have, and then that's being handled in the conventional way using the good old Flatmap idiom that we all know and love from Project Reactor and RxJava. And we are changing the threads to run in the custom pool. So we're setting what that pool is, and that pool, as you can see, is being set up here. I'm just choosing to use the new parallel pool so I can get explicit control over the number of threads in it. I could also, of course, choose to use an elastic pool, which auto scales and grows and shrinks and so on. But I just wanted to get very fine-grained control over that. Ignore is not the same as drop. Ignore basically says back pressure is happening, but just pretend like it's not happening. So we'd have to go take a look. Let's go see if we can find the documentation for ignore and see what it says. Be over here. Okay. Completely ignore downstream back pressure requests. This may yield illegal state exception when queues get full downstream. So this is kind of like everybody's favorite analogy for back pressure is a famous, I think it was I Love Lucy episode where she and her friend are working in a chocolate factory or a pie factory or something like that. And the pies or whatever it is coming down this conveyor belt faster than she and her friend can get them and put them in boxes or stack them or something like that. And so this classic example is just saying, if you go back and watch the video, it's pretty funny because eventually first they start trying to eat the candy or the pies or whatever, and finally they're just like throwing them on the floor. But the point is that ignore is kind of like what they're doing. They're not controlling the back pressure at all. I guess they're kind of doing drop ultimately. But this is just saying, I'm going to take my chances. Maybe I'll get lucky, maybe I won't. Probably not the best option to use if you want to write robust code. By default, the data channel is closed when the error occurs. Not sure if we could still emit after error. The particular problem that I'm running into here is a little different. It has to do with an exception being thrown and not caught properly, and therefore the thread is evaporating before it's completing. So I think I have a way to fix it, but I just didn't have time to do it before today. Basically, the emitter thread decides on which thread the pipeline will run. Well, sort of. So what it's really doing is saying, let's go take a look at the code just to be very clear about what we're saying. So if you take a look over here, you can see that we're always running the publisher on its own thread. So it's always running in its own unique thread. It's not being shared with anybody else unless we set that option to turn off parallel processing entirely. And so if you see down here, the publish operation, which is defined here, subscribes on the schedule that's passed to it. And what that does, if you recall how the semantics of subscribe on work, that means we go upwards in the stream and everything will be generated initially in that thread, in the publisher thread, starting with the stuff up here. So we're going to basically be emitting on the publisher thread. But then once we get into the real flux pipeline that matters, this one here, the Flatmap, when that thing gets run, that's going to end up using publish on. So again, if you recall your publish on versus subscribe on semantics, once publish on is called, then everything from that point downwards until either subscribe is reached or there's a different publish on, all of that is going to be handled in different thread or threads. And of course, whether it's a thread or threads depends on the parameter that we pass in when we made that subscriber thread pool, which we did up here. Let's see. Yeah, so when we call the subscriber thread pool, we give the parallelism count at that point. So that's basically kind of the steps involved here. And this is a very common model, right? So if we don't go and use the Flatmap trick, then we're only going to have one publisher and one subscriber. And that has to do thread, one publisher, one subscriber thread. And that has to do with the semantics of the contract for basically on next. On next always has to be called in one thread. And so what we're doing by using this little trick here is we're still honoring that, except now we're splitting up the input into separate streams, all of which run in parallel and all of which emit in their own private thread, if that makes sense. So that's basically how you get parallelism. One of the ways you get parallelism in Project Reactor and RxJava is by using the Flatmap trick. You could also use a parallel flux or a parallel flowable if you're in RxJava, but that is not as transparently tunable the way this example is, because you can't change the count programmatically without having to go back and change the code. So the Flatmap trick is, in some sense, more configurable. Is the Flatmap trick or publisher? So you use Flatmap like we're doing here. So the question is it the Flatmap trick or publish on trick to run in many threads? It's the combination. So you use Flatmap, and then each of the inner publishers, which is what we're doing here, we have many inner publishers. Basically, for every number in our stream, we have an inner publisher, and that's going to publish that number. And then in conjunction with publish on, now we get it to run in many threads. That, of course, all is premised on the fact that the subscriber scheduler is set up with a thread pool with multiple threads attached to it. If we only have one thread, then it's obviously just going to run in one thread. But if we have a subscriber scheduler with many threads, which is what we can do here, if we turn on the command line options properly, then we can have it run in a pool of threads. So I think what's pretty cool about this is you can kind of decide the degree of parallelism you want, and it's very much under your control. You can take full control over that, as long as you know the idiom or as the pattern or whatever you want to say. Okay, so those are really the things I want to talk about today. As you can see, the example keeps getting more and more intricate, and I found it very useful because I can do apples-to-apples comparisons between different strategies fairly easily without having to write 17 different versions of the code. The downside, of course, with getting so clever is that this code becomes complicated, so and heavily parameterized. Okay, so let us go ahead and switch back here. So as we kind of wrap up, last question that I saw was, what's the agenda for the future? And what I want to say is the following. So we will continue doing these sessions. What we're covering may depend on a few things. There's a chance I'll be teaching a C++ class this summer for Vanderbilt students. And so if that's the case, I'm probably going to switch over to preparing and test driving my examples for that course. So that's what we'll probably do. If that course doesn't go forward, and it may or may not go forward, then we'll continue marching through other cool examples relating to synchronization, relating to completable futures, relating to parallel and sequential streams, reactive streams, Project Reactor most likely. And I'll continue to learn more about stuff. There's a whole gobs of other things with RxJava and Project Reactor I'm just beginning to explore. So we'll probably continue to cover some of those things as well. There was another question that just popped up having to do with let's see, parallel flux. So in this particular example, as you can see, we're basically doing a parallel flux, but using the Flatmap publish on idiom instead of using parallel fluxes. Parallel flux is more effective for certain kinds of situations when you know you want to run things in parallel. This particular example, just for teaching purposes, I wanted to be able to toggle back and forth between sequential and parallel processing. So I chose the Flatmap publish on trick or idiom as opposed to parallel flux, which I could use, but it's more obtrusive. Both of these examples sort of end up joining things back together, but one of the things that with parallel flux that you really want to be able to do is you want to be able to go from parallel processing to sequential by the dot sequential operation. And then oftentimes you want to be able to essentially collect the results together. Now, in this particular case, we weren't really collecting the results because we were just computing whether they were prime or not. But in other programs that we've looked at in the past, we actually wanted to get the results and put them someplace, like into a collection of some type, like an array list or whatnot, or a set. So in that particular, or perhaps if we're doing numeric computations, we want to be able to sum the results or compute an average of the results or whatever. So those are situations where you can use the parallel flux mechanisms quite nicely because they can be used in conjunction with other RX Java operations like collect, which works just like collectors in Java streams, or you can also use them with reduce. Having said that, you can also do those kinds of things with the Flatmap trick as well. So I think they're pretty much the same. It's just the parallel flux approach is more for people who want to make it very clear that their programs are running in parallel. Whereas the Flatmap idiom, it's a little bit obscure. Once you know it, you recognize it from a mile away. But at first, it's like, it's a lot of extra work. If you build a few wrappers and use transform or transform deferred, you can hide it a bit. But it's a bit more overt or explicit, if you will. So parallel flux just makes it really crystal clear what you're trying to do. Okay, well, again, everybody, thanks so much for coming. Great questions, as always. I will go ahead and put this video out shortly, and hopefully have a good weekend, and I will look forward to seeing you next week.